Hello, it's Keith here, and this is the first in a new series of videos I'm going to be doing, in which I'm going to be looking at the source code of the ChibiAkumas game, discussing some of the technical choices in the programming, and showing you how to actually change the game to make your own game or to tweak it to do different things to the way it currently works. Now, ChibiAkumas is of course open source, and later on I'll actually be creating a special game just for this series, which is fully documented, the source code's fully commented, and I'll show you how to make changes and change the level and make your own levels and sprites and things, so you'll be able to make your own game using my game as a basis. As I've said before, ChibiAkumas is completely open source, and I fully encourage you to use the game, the sprites and the characters to whatever extent you wish in making your own game without restriction. So hopefully that'll give you something to start from, to make it a bit easier for you to get into programming and to make something that you can really quite justifiably be proud of, making something of your own without having to worry about all of the technicalities of writing your own sprites and disk loaders and things like that. So anyway, let's make a start. So you can see we're looking at Tragical Chase here, which is my new game, which is a very small, simple game, and that's going to be the basis of this tutorial series for now until I can finish the new game, which eventually will be released along with this series. But the two are going to be very similar anyway, so it doesn't really matter. Now today we're going to have to start at really the beginning, and I think the first thing we need to discuss is the way that screen coordinates work within ChibiAkumas. The reason it's so important is because it's not just drawing sprites to the screen that the coordinates are important, but it's also actually the movement of the object, the movement of the bullets. Really everything is designed around the screen coordinates, because it's from those coordinates you can do bullets, you can do collision detection, you can do player sprites, you can do game sprites, and then of course you can do object movement. It all comes down to the coordinates. So I wanted to discuss that today. We'll then move on from the graphical screen coordinates to the simpler text coordinates, and then we'll actually, just for a bit of fun, we'll look at the source code of the text drawing game code, and we'll learn how to actually add some text to the game and print it to the screen using the ChibiAkumas game engine. Now, if you're not familiar with it, the ChibiAkumas game engine is called Akuyo. That means something like misuse in Japanese, the reason being that I considered it a bit of a misuse of my time creating a game on an 8-bit system in 2017. So it's a bit of a joke name, and it was basically the working name of the game before I was fully happy with the ChibiAkumas name for the game. I sort of came up with the name ChibiAkumas very early on in development, but I wasn't sure if I would decide it wasn't that good and I'd come up with something else. But I needed a working title within the game code anyway, and so I decided to use Akuyo because it was a nice short name for code, because it's sometimes used in the name of the modules and things. But it was vague enough that if I decided to call the game Chibi Monsters or Little Akumas or something, it wouldn't have made any difference. So it was kind of the working title of the game, and it's also the name of the current game engine. So anyway, let's make a start. Just move this out of the way. So how does ChibiAkumas work with screen coordinates? Well, the Amstrad CPC was the original system for ChibiAkumas. It was ported later to the MSX and the Spectrum and the Enterprise. So all of the game's internal workings were designed around the Amstrad CPC. I decided very early on I wanted to use Screen Mode 1. Screen Mode 1 is 320 pixels across by 200 pixels down. Okay, well, the important thing you need to think about with regards to 8-bit systems, and with regards especially to ChibiAkumas, is an 8-bit system is designed to work from 0 to 255. So when you're working with a screen coordinate that goes up to 320, that immediately puts you in a bit of a difficult situation. And there's two reasons for this. Firstly, an 8-bit system is fast at 8-bit mathematics. So if you're trying to work with values that go up to 255, it's going to be quite fast. If you go over that 255, say to 320 or 65536, which is a limit of a 16-bit number, it's going to be much slower. So you don't want to do that. Especially you don't want to do that in a game like ChibiAkumas, where there's 255 bullets on the screen. Because if there's 255 bullets on the screen, any calculation you do is going to be multiplied by 255 times. So even a few small slowdowns with regards to more complex mathematics are going to have a big end result effect on the speed of the game. So it's always, what can I do fast, and then what do I want to do? That's kind of the priority of working out how you're going to code the game. Now, that's the technicalities of the processor, but there's also technicalities of the screen of the Amstrad CPC. As I've said, it's 320 pixels wide, but it's 2 bits per pixel, and what that means is 1 byte contains 4 pixels within it. So again, we've got very serious speed limitations, and so really the sprites needed for speed reasons and for memory reasons to move in 4-pixel chunks, which mean the x-coordinate would go up from 0 to 80 because there's 80 bytes across the screen and 200 lines down. So you'd have kind of a mathematical area of 80 times 200 if you were working in byte blocks. And that is what the sprites generally do in ChibiAkumas. Now the bullets, that wouldn't be enough for, and so the bullet code has special code that can work at higher resolution. There's no sprites for the bullets in the Amstrad version. It's actually fully coded, so it's doing it at the byte level, purely in assembly. It's not really a compiled sprite because it's too small to be referred to as that, but that's kind of the way it's going. It's code that has the effect of sprites. It's not sprites. So that's the thing there. Now, when I was thinking of this and working all of this out, I knew that 80 by 200 wasn't acceptable. I knew because it would be too low resolution for the bullets. I knew that 320 by 200 would not be acceptable. That would breach over the 256 limit of the byte values. So what I came up with is a screen size of 160 across by 200 down. And so the virtual screen within ChibiAkumas, all of the coordinates work 160 across, 200 down. Now, if you're working at the byte level, you just ignore the least significant bit, and you've got down to 80 by 200, which is you can use for your byte coordinates of the screen. The bullets will work at 160 because there's two versions of the bullet drawing code, depending on whether it's on the left-hand side of the byte or the right-hand side of the byte. So that's how we get around that. Now, beyond that, there is another consideration that we needed, and that is we need the sprites to be half on or half off the screen. So starting with the top left corner of the virtual screen 0,0 being the top left corner of the physical screen 0,0 would make it very difficult for us to draw a sprite that's half on or half off the screen. And as you know, if you've played the game, the enemies will come onto the screen and then go off the screen. So while the Chibico player sprite never goes partially off the screen, the enemy sprites do. So I needed to have some facility for that to work. Early on in the game, when I was designing it, I'll just show you here some of the sprites. Now, a lot of the game engine itself was really designed, so to speak, on a piece of paper and with a calculator. I worked out all of the kind of concepts I wanted to use, worked out if I believed they were viable early on, just with scraps of paper, working things out on a calculator. And one of the important things that I needed to work out when I was doing this kind of thing is how big did I think the sprites should be for the enemies. Now, it was basically just, well, I kind of worked out how much memory I'd think I'd need for the levels, how much of it would need to be code, how much it would need to be sound effects. And so then it was down to, well, how big a sprite do I need? Well, they've got to be as big as I can make them, but if I make them too big, the game will slow down or I'll run out of memory. And so I came up with the idea of 24 by 24, and you can see that here, for the sprites, as a good balance between 16 by 16 is too small, 32 by 32 is going to take too much memory. So 24 by 24 is the basic sprite, and each sprite has 2 frames of animation, generally speaking. Now, the reason for this is the 6128, the game supports the Amstrad CPC 6128, and it uses 2 banks on that system. But I also wanted to support the 48K, and I wanted to do it in a way where I could kind of slice off some of the functionality without the gameplay being massively reduced. And so what I did is I use 1 bank on the 64K, 2 banks on the 128. So the 128 is better, but the 64 is basically the same game. So most of the sprites are 24 by 24, but you'll notice some of them aren't. This one's 32 by 24. And in the original game, the collision detection for the bullets didn't work on those kind of sprites, but it does now on the episode 2 and version 1.666. So anyway, one other thing I will just show you if I can find a background. Now you'll notice here there's a moon. And if I press next sprite and if I press next bank and last bank, you'll see that it's shifting by 2 pixels. As I said before, the virtual screen is 160 pixels wide, but the physical screen is only 80 bytes across. And I can't, in software, shift the pixels by a half byte. So what I've done is I've stored 2 versions of the background sprites so I can shift them at half resolution. And that's how we do it. And again, that's a 128K only feature that possibly you haven't noticed. So that's how I get around the limitation of having to move the sprites in bytes, which, as I've said, I could have written code to do a real-time shifting of the bytes, but it would have been so slow it wouldn't have been viable. So that's not something that the game engine does. Now, once I'd decided that the sprites were going to be 24 by 24 pixels wide, this gave me the ability to decide how to do the clipping, which is where the sprite is half on the screen and half off the screen. It's very simple the way it's done. because I've got a visible virtual screen of 160 across and 200 down, I was then able to add a 24 pixel border around that, so that the virtual screen goes from 0,0 to 208,248, and there is a 24 pixel border around on all sides of this that is not visible, and this allows the sprite to be off screen, start coming on screen, be completely off screen, and then as it goes towards the other end of the screen, go off screen again. So that's how the coordinates cope with the clipping area. Then when the game was ported to the MSX and the Spectrum, those systems have a smaller screen. The Amstrad CPC is 320 by 200. On the MSX and Spectrum, it works at 256 by 192. So you're losing some area of the screen. And so what I ended up doing is, you can see this smaller green screen here, and this is the area used on the MSX and the Spectrum. So you can see here an area of 32 visible pixels or 16 virtual units has been removed from each side, and then one line of 8 pixels or 8 virtual units has been removed from the top, and this is so that objects that move on the ground would still be in a consistent position, but generally speaking it would be showing the center area of the screen. And you can confirm this yourself if you play the two versions of the game on the CPC and the MSX, for example. You'll see that the enemies come on slightly later, and you can actually shoot them when they're off screen, because the virtual screen coordinates are being used in all cases by the game engine. So this did cause some problems. Some objects had to be moved around a little bit to make them still work properly once the game was ported to the MSX and Spectrum. But as I say, it worked very well in general. So you can see here, this is how, these are the coordinates the game engine uses for placing objects. This is the area you can see on the Amstrad CPC, and this is the area you can see on the MSX and Spectrum. So that's how the coordinates work, from the game's virtual coordinates to the physical on-screen coordinates. Okay, so that's all pretty simple. Now this did cause some challenges for the Turbo R version, which was one of the last sort of versions I created. When the Turbo R is very, very fast, and because it's got the V9K added to it, it allows for very advanced flexibility with regards to movement. Very slow movement will still be very smooth. Unfortunately, because the game engine could only work in 2 pixel chunks, even if I rewrote the graphics sprite drawers, I couldn't get any more definition because the game engine wasn't providing it. So this is that was one of those times where the limitations that you designed in at the start end up sort of biting you later on. Unfortunately, when you're doing 8-bit coding and when you're doing it as an amateur with limited time, you kind of have to make decisions at the start and then live with them at the end, because you can't rewrite your entire game engine just because the Turbo R V9K version could work better. It's just not possible. So as I say, you kind of have to get your calculator and your paper out and work things out as best you can in theory at the start, and then there comes a point where you've gone too far, you've put too much time into that model that you can't rewrite the entire game engine just because the Turbo R with the V9K turns up 2 years later and would have preferred an alternate model. So it's just what you have to live with. Now, the text coordinates don't work the same. They work much more simply, and that's because there's no clipping of text coordinates. So the text can't be half on and half off screen. So we're working in a much simpler model there. The way it works is it works in the exact same way as the Amstrad CPC version works. It was originally written that ChibiAkumas used the firmware fonts and the firmware text drawing code. However, that's very, very slow, so it's completely non-viable. So when I wrote the replacements that use sprites, it's the same sprite engine that draws the graphics as the fonts. I wrote it to work in the same way as the Amstrad CPC one. The CPC text screen uses 40 columns and 25 rows. So again, this causes some problems for the MSX. And again, what I decided to do was keep the center of the screen, but this time removing the bottom line, because I thought that would be more appropriate with regards to making the CPC and the MSX work as close as possible between the two, where as little stuff needed changing as possible, because most text is centralized, and I figured the bottommost line was probably the least important. So this has the effect that the left foremost and the right foremost columns are removed from the MSX, so we can't use those unless we're going to write different code for both systems. And the bottommost line is removed from the MSX. So this is the MSX visible text area, and this is the text area of all of the CPC as well, and the Enterprise, of course. CPC and Enterprise do have the same screen area. So there we go. So that's the concept of how the screen works with regards to text and sprites. And we're going to look at sprites and how to create objects in the game level and things like that later. But for today, what we're going to do is look at something fairly simple and self-contained. We're going to look at how the Amstrad CPC's fonts are drawn to screen, because I think maybe that'll be a little bit interesting for people who aren't interested in the theory but want to see a bit of Z80 coding. So let's have a look at that now. So this is the text driver for the Amstrad CPC, but generally speaking it's going to be quite similar for the other systems. Now all of the systems except for the 64K Amstrad CPC use a sprite based font, and this is what it looks like. This is the sprite based font. You can see it's got a set of symbols in large font, and then it's got a miniature font set of symbols. So this is basically what the ChibiAkumas game engine uses, and you can see it just here. Now, one important thing to notice is it starts at number 33. Unfortunately, I didn't put a space in. This was because when I was writing the original game, I was so limited for memory, it didn't seem a sensible use of memory. So I took it out, but it did make coding things a little bit hard, and that's why the configure control screen uses minuses rather than spaces to blank out the previous control option, because there is no space. I did have to write one in later, a special routine to draw spaces to do the cursor on the menus, but it was a pain, so I should have put a space in. And you'll see that the font that I use in my tutorials does have a space character in it, just because I realised what a stupid idea it had been not to put one in. But it's, again, do I recode all of the font routines, redo all the sprites, or do I just live with it and keep going? Well, in most cases it's a case of, well, I don't really have any more time I can justify putting into this game, so I just live with the limitations. So that's the font. So how does the text drawing work? Well, passing a text string to ChibiAkumas works like this. As I've said before, the location of the text cursor will work in Amstrad CPC type coordinates, where the cursor position is passed in a HL, and we use a command called locate sprite because we're doing a location command for sprite based fonts. We then have a font we can select. There are two fonts. Font 2 is the large font, which you can just see here. Well, what's font 1? Well, font 1 is the miniature font, which you can see in the middle of the screen here. This was used for the interactive insults in episode 2, where the characters would throw abuse at each other in the middle of the game. I needed a much smaller font for that, so that's what that is. You'll see here there's a command called draw, locate and print string unlimited. What does print string unlimited mean? Well, generally speaking, ChibiAkumas, when it's drawing text to the screen, allows you the I register to be used as a temporary store for a maximum number of characters. So if I is 1, then it will only print 1 character. If I is 255, then it will print as many characters as needed, because the text on the one line will only be 80 characters maximum. So this is used by the warning messages in the boss battles. The text would type itself on screen, and so what you did is you incremented I progressively every time you drew it, and this would make the text type onto the screen 1 character at a time. But it's hard coded into the system, and in most cases you won't need that. So print string unlimited doesn't use that kind of limitation, but the regular version does. So you need to set the I register to 255 or something very high if you want all of the text to print. But if you want to have that typing effect, you need to control I every time you run the module. So there we go. Now you can see here there's a character 80. This is a kind of oversimplistic version of this definition. If we want to define text, what we would usually do if we were being memory efficient is this. Now we would add 128 to the last character, and this saves us a byte, because a character return or a character 0 terminating the string would take an extra byte. But if we add 128 to the E, then the E can be detected as the last character in the font, in the text, but we don't waste a byte in the process. Now I've been lazy here with this wave command because memory wasn't a limitation, so I've just used an 80 byte. This did, however, cause me a problem with regard to the Japanese version of ChibiAkumas episode 1, because then I needed more characters than there were left between 32 and 128. So what I did on the Japanese system is I used a character 255. So instead of adding 80 to the last character, you would just put a 255 at the end. So this would use more memory, but it would allow me to support character sets with far more characters. The reason this wasn't a problem on the MSX is because the Amstrad CPC is actually the largest version of the game. Because of the 64K support and the requirement of supporting 64K on the Amstrad CPC, there was an extra code to do that 64K support, as well as the plus sprite support, that simply didn't exist on the MSX. So while memory is quite limited on the CPC, it's not so limited on the other systems. So you can see here we're checking if we've reached the last character, and if we have, we use a special print last character command, and what this does is it removes that 128 from the character before printing it. Draw text jar sprite will do exactly what it sounds like. It draws a single character to the screen. And then we've got a loop here because we're just going to continue around until we get to the last character in the string, which would be this, and at which point we'll return. So here's the print string command, and you can see here we're checking the I register and we're seeing if we've reached the end. If we've reached the end, then we just finish, but otherwise we print the characters. We've got again here in this version of the code, we're just checking whether we've reached the last character or not. And we've got a special protect BC command here for draw text char sprite, just to save a little bit of memory there. Now when we get to the last character, we need to remove that 128, and we do it with an AND command here. And again, we're just printing the character to the screen. And here what we've got is we've got some decimal code. Now with things like the continues and the countdown for continuing, these aren't using binary coded decimal. So what this function does is it takes a 3-digit value from 0 to 255 and it breaks it down by division into its individual digits, and it will print that code there. It actually uses a bit of self-modifying code here, because if the digits you want to show is 3, it will just show 3, which means you have to skip the first two zeros. But if it's 103, you need to show that second 0, and so this is checking if the first digit isn't 0, then it will show that second 0, but if the first digit isn't 0, then it won't. And so that's what that's doing there. It's effectively changing a call non-zero to a call in self-modifying code. And then when we get down to here, we're just printing the sprite to the screen as usual. Okay. This is another special function which allows for carriage returns within the text string itself. This effectively means when a locate command is done, the location position is backed up, and then when a carriage return symbol is found, that location position is read back, and a 1 is added to the Y coordinate, meaning that we are now starting again at the line below the last one. So this is used in some cases in the game engine just to make getting text to the screen a lot quicker. So how do we draw the text to the screen? Well, the first thing we do is we take in the Y coordinate and we multiply it by 8, because we're working in 8 by 8 pixel fonts. So we multiply the Y coordinate by 8 and store it in sprite show Y. Sprite show Y is the variable used by the sprite drawing routine, which will do our font. Then we need to subtract the skipped size of the screen. Now on the Amstrad CPC we don't need to do that, but on the MSX and the Spectrum we do need to do that. So this will effectively subtract 4. Then we store the X coordinate here. So here's the actual draw text char sprite. This shows a single character to the screen. Now on most systems this is going to use a sprite font, but as I've said before, on the 464 then there's not enough memory for that sprite font because it uses a total of 4 kilobytes. So what it uses is the firmware's built-in font in the ROM, and it has to do that in a rather tricky way, which we'll look at in a moment. So first we're checking if we've got a character return here, and if we have, then we need to process that. The move size is 2 because we're moving in 2-byte chunks. Now at this point we're going to subtract 33 to get to the first character in our font, because the first character is character 33 here. Characters below 33 do have special functions. Some of them are used in the interactive insults to change the position of the text, which player is talking, and they can also in some cases change the font and things like that. So anything below 32 is reserved for system functions. So anything above 32 is a visible font up to 128, which is considered the end of the line. So next we need to work out our screen coordinates. So we're loading in the last screen coordinate used, and we're checking if we're now off the screen, and if we are, then we finish. Of course the screen size is different depending on the system. Now we need to move along by the size of our sprite, and then once we get to here, we need to just check if we're showing any unusual characters. Because we did a sub 33 here, if at this point if we're above 192, then we're trying to print a character that isn't a visible character. So we've got to return here just to check that. Now there's some self-modifying code here. This will be changed on the 64K systems into a jump, and we'll look at that later. If we're not on the 464, then what we need to do is bank switch in the font bank, because it's in one of the 128K banks. Switch the bank, call the show sprite direct function. The show sprite direct is for fixed width sprites. It can't do clipping and things, but it's faster. And then we bank switch in the original bank that the code had in before we did that font. Now that's all we really need to do on the non-Amstrad CPC 464. Now when it comes to the CPC 464 font, we are going to have to do some tricks. We don't have enough memory for the bitmap font, so what we're going to use is the internal font of the firmware. This is unfortunately quite tricky for a few reasons. The first of these reasons is the memory. The core game code, which is what you're looking at here, is stored in the first bank of the system memory from quadruple 0 to 4000. This is the same memory bank that the ROM has to be paged into. So what we're going to do is we're going to page the ROM into the same position as our code and read out the font. That's not going to work very well. So what we do is we copy the bytes of the character we want into some spare memory at the top of the screen memory area to do the work. Okay, but that's not even enough. We need to actually write some code into some spare memory to page in the ROM, read the font, and then page out the ROM, and then return execution to the code that was in the memory the ROM was just paged into. Because if we page the ROM in, our game will immediately crash. So that's what we're having to do, just because of the really restrictive memory limitations that you're under when you're dealing with a 64 kilobyte system, which has two 16 kilobyte screen buffers. Okay, so this is what we do. So we work out the byte position of our screen, and then we work out the position of the character that we want to read in. This is the first character in the ROM, and of course we only want the 33rd character because our font has no space. So now we've got HL with the correct starting position of the ROM font. And now we're multiplying up DE because we have 8 lines per character, and we want to get the correct position of the character that we want, and that's what we've done here. So now we have the memory location of the font we want, and then what we need to do is we need to actually copy the code that's going to do the work into some spare memory at the top of the memory area here. This is actually the end of the screen. It's not used by the screen, so it's not going to harm anything. So we copy the chunk of code to this area, and we're going to call it in just a moment. At this point, we're going to select another piece of spare memory in the screen area to store the destination, which is going to be the bytes of the character we want to draw to screen. And then we call the copy we made here. And let's have a look at what that code does. Well, it's very simple. It pages in the Amstrad CPC ROM here using this command out into this port here. And then it copies the 8 bytes with an LDI. LDI is faster than LDIR, remember, and we know we only want 8 bytes. And then we turn the firmware off and we return. Notice there's no jumps in this code here, because this code here is going to be run from a different memory address to the one it's stored in here. So if there was a jump, it wouldn't work correctly. If there was a jump to get char, for example, it would actually malfunction because the code isn't going to be run in that memory location. And if there was a jump to get char, when it was actually executed, the ROM would actually be covering it. So again, you would get a crash. So when you're relocating code, you need to be very careful on the kind of command you use. JP wouldn't work because it's an absolute jump. A relative jump would work. But if you're not sure, just don't mess with them. This kind of relatively code isn't something you really need in 8-bit programming very often. So it's probably not something to worry about. So, okay. So now we come to this piece of code here. So we've got the regular version here and the half-width version here. So what we need to do is split up the bytes that we read from the firmware font. The firmware font is 1 bit per pixel, but our screen is 2 bits per pixel. So we need to split the nibbles in half and store them to the screen in 2 separate chunks, shifting one of the nibbles correctly for the screen format. And this will get the code to the screen. Okay, now that's pretty straightforward for the normal font, but the half-width font is a little bit more tricky. Again, we've got no memory to store a bitmap font. So what we're having to do is we're having to load in the bytes of the firmware font and then shift them around, missing half of the nibbles, so that we've effectively got a half-width font. And again, we show it to the screen here. So this code here is all exclusive to the Amstrad CPC 464, and that's why I said the Amstrad CPC 464 version is bigger than the other versions, because of all this special code designed to work around the memory limitations of the Amstrad CPC 464. It becomes a paradox that you've got extra code on the system you can least afford extra code. So there we go. So let's have a look at an example of actually using it. Well, what we're going to do is we're going to have a look at something called the Bootstrap. The core of the ChibiAkumas game engine is kind of split into two chunks. The first is the core itself. This is loaded into the first 16 kilobytes of the system memory on the Amstrad CPC. It handles the main game loop, the reading of the controls, the displaying of fonts and graphics on screen. It handles the sound and things like that. The Bootstrap is an extra module that's loaded in as required. It's loaded into the second screen buffer. So when the Bootstrap is in memory, you can't use two screen buffers. This is why some parts of the game don't have as nice graphics like the continue screen, because that's part of the Bootstrap. So you can only do very limited graphics, and you can't do nice animation and things when you've got the Bootstrap in memory. The Bootstrap handles loading of the levels, initialization of the game, the continue screen, the game over screen, and the redefine keys screen. So it's really the extra module of the core that couldn't be fitted into the core because of memory limitations, again on the 64K systems. So what we're looking at here is level 0. Level 0 is the menu. There is no level 0. Level 1's the first level. But all the extra routines, like the introduction screen, the menu, these are all levels in some sense, as the code considers them. So what we're going to do here is we're going to have a little bit of fun, and we're going to show a version number on the top of the screen. We've got to be a little bit careful when we do this. If we showed it as soon as the loading screen appeared, then it wouldn't work, because we actually have to have the font in memory to be able to show text on the screen. So we're going to show it as the level loads. So the first thing we need to do is we need to select our font. We're doing this, we're selecting font 2, which is the normal font. Then we're going to set our I register to 255, because we want to show as many characters as possible. We're not going to use LDI, A, because while this works fine on the MSX and the Amstrad CPC, we aren't actually using the real I register on the Spectrum, because on the Spectrum we're using interrupt mode 2, and that needs the I register. This is one of those times where I did something on the Amstrad CPC that seemed fairly efficient, making use of a spare register to store a value, but on the ZX Spectrum it's a complete disaster, because I needed that for something else. So this LDIA macro will convert to the real command loading into the I register on the Amstrad CPC, MSX and Enterprise, but on the Spectrum it will actually use a temporary piece of memory to store the value that would have gone into the I register. Next we need to select a text position. We're loading H with the value 4, which is the leftmost visible position on the MSX, and it's just slightly indented on the Amstrad CPC. And we're selecting the top row here, 0, which will mean this will appear in the top left hand corner. And what we're going to show is a version number here that's denoted by this memory location here. And you can see here it's terminated by adding 128 to the last character we're going to show. Now we load that in to BC, the address of that string, and then we call print string here. You'll notice here that this prefix of Akuyo underscore on all of our calls. What's that? Well, there is a jump block to the Akuyo game engine that all of these are defined in. And you can see that all of these will work anywhere in any module. While the game engine changes with regards to the actual code within the core, the jump block is constant. So you can call these from levels without having to worry about whether the core has been recompiled. With the Bootstrap and the core, they're both recompiled at the same time, so you can use any module in the core in the Bootstrap, but when you're doing the level code, you can only use the modules that are exposed by the core's jump block, and that's why we're using these Akuyo commands here. So we're going to select the font, locate the cursor, and then print the text at the cursor. And so this altogether will print our text version number to the top of the screen. So there we go. So that's the theory. So how do we compile it? Well, when you're recompiling the core, because the Bootstrap is part of this core, what you need to do is enable the correct directive for the system you want to compile. So I'm going to compile for the CPC, and then we just do our assemble. And if we get no errors, which we did, then we can just try it out. So you can see the game is now loading. Speed things up a bit. And now you can see our version 1.00 is in the top left-hand corner of the screen. Now, the benefit of using the Akuyo game engine to do work for us, as opposed to doing something like getting the firmware to do it for us, is we can now compile this onto any system that Akuyo supports. So let's change that CPC directive to an MSX directive and compile again. Again with WinApe, all versions of Akuyo have to be compiled with WinApe. It won't compile with Vasm. And now let's run the MSX version. You can see it was just updating the disk image there. And again, let's fast forward things a bit. And you can see now the version number is showing as well on the MSX version. And so that's the benefit of using the game engine to do the work for us, because as I've said before, the game engine is designed to be multi-platform, so you can do things in a common way on all the systems. And let's just try changing the font to number 1 here. Let's do file save all, because we need to make sure that Bootstrap file is saved. And let's just start the game again. And now you can see the font is the narrow font. And so there you go. So we've looked at quite a lot today. We've had a look at how the screen coordinates work within ChibiAkumas, which is going to be very important in the future when we start to look at how the bullet array code works and things like that. But we've also looked at how the fonts work in source code and how to actually program ChibiAkumas to show extra fonts on the screen if we want to have some fun and put our own text messages in. So there we go. Hope you've enjoyed today's lesson. Please like and subscribe, because I'm going to keep making them, and eventually you will be able to download the source code for a whole new game, and we will actually look at how to reprogram that source code, how to make our own sprites for it, and so you can reskin it and reprogram it into whatever game you want to create. Anyway, thanks for watching today, and goodbye.